This one also we have discussed. In the first stage, elastic stage, this will be your stress diagram, and corresponding moment of resistance will be your that will be less than or equal to your yield moment. Yield moment is nothing but your sigma y into elastic section modulus. And after that, the stress diagram will be like this. It will be partially elastic and partially plastic. At this stage, your moment of resistance will be somewhere in between your yield moment and plastic moment. And at the fully plastic stage, your stress diagram will be rectangular. It will be just like rectangular stress variation, and corresponding moment of resistance, that will be your plastic moment of resistance. And in this stage, every fiber has reached the yield stress value. Okay, so I think up to that we have discussed. So we will continue from there. So after that, we started discussing about plastic hinge. Okay, the plastic hinge, that means the plastic hinge means so it is nothing but at the ultimate stage, what will happen? Your stress will become like this, and this stage, and that it is happening at a cross section. At a wherever, suppose if we have a simply supported beam with point load, wherever a point load is acting, that is a cross section where we have maximum bending moment. And if we keep on increasing load P, the bending moment at that section will be keep on increasing. Every section moment is increasing, but that section will have maximum moment. So that means this section bending moment will reach plastic moment first in the simply supported beam. Okay. So once it reaches plastic moment, what will be the corresponding stress distribution? It will be like this. So it is fully yielded. Every fiber has reached the yield stress. So that it is the that yielded zone due to flexure in a structure, that is known as plastic hinge. So once the stress distribution became in this stage, it has reached this state, and that cross section will be calling that is a plastic hinge. Okay, so why we come calling it as a hinge? After that, what will happen is at that point it is going to act like your physical hinge. The physical hinge means, suppose if we have a hinge support, what is the specialty of that support? It will not have any resistance against your moment. If you apply some moment, it is free to rotate. It is free to rotate. Okay, and once the cross section reach this stage, and after that, that cross section will also behave like a hinge only. And but the stress distribution at that section is fully plastic. That is why we are calling that section that yielded zone. A completely yielded zone of your beam will be calling the plastic hinge. Okay, but what is the difference between the plastic hinge and your mechanical hinge or your physical hinge? A physical hinge, I mean the support only. Okay, hinge support. Okay, or you can say internal hinge or something like that. So what is the difference? And if you have a simply supported beam, let us take a simply supported beam. Let us take a simply supported beam, and we apply some loading. So it is going to bend, or it will be like this in the elastic stage. And at this stage, it is having rotation. It is free to rotate. And the supports are free to rotate, but your bending moment is zero. At the physical hinge, the moment is zero, and it is free to rotate. But when you come to the plastic hinge, the moment is not zero. So finally, the plastic hinge, here I have plastic hinge in this case at the point where we have maximum moment, and here your bending moment is not zero, but your moment value will be equal to plastic moment. So that is the difference between your physical hinge and your plastic hinge. Okay, both are once the cross section has reached this stage, and after that, it will not have any more resistance. Again, it cannot resist any further bending moment. That is its maximum. After that, if you apply the moment, what will happen? It will just free to rotate. Okay, and that is why once the plastic hinge has formed, your beam, there will not be any more bending actually. Finally, what will happen? Here a hinge will be forming at this stage. A hinge will form at the midpoint. And now you see, I have two hinge support already here, and I have another hinge here. And now if you apply subload, what will happen? It will just deform like this. That is why at the plastic state, once the plastic hinge has formed in this structure, what will happen is there will not be any bending like this. Instead of the bending, it will just deform like a rigid bar only. because it is connected with three hinge finally, so it will not bend, it will just deform like a rigid bar only. Okay, but up to that stage, during the elastic stage, it will have bending. If you keep on increase the load, your bending, your deflection will be keep on increasing. And if you want, you can find out the deflection values by using any of your elastic theories. But at the moment it reaches this stage, and finally a hinge will be forming, and after that it will be just deformed like a rigid bar only, like this. You can see it will be a straight line. It will not be. It will not have any bending there. And corresponding to this stage, what is the moment of resistance of that section? That is known as plastic moment. And this location of your beam is known as the plastic hinge. The plastic hinge is simple way. You can say that the completely yielded zone of your structure. So I will discuss here also again the plastic hinge. So here we can see it is we are applying a concentrated load to the simply supported beam, and this will be your moment diagram. Okay, and moment is maximum at the point of action of your load. Okay, so this at this section, your plastic hinge will be forming at this section at the bed span. Okay, so when the stress distribution reaches fully plastic, the plastic hinge is said to have formed because because it has no additional moment can be resisted at that section. Okay, once the plastic hinge has formed, it is this is the plastic hinge location. Okay, the once the plastic hinge has formed, it is the cross section will not have any more resistance. It cannot resist any additional moment. And if you apply once the plastic hinge has formed at the midsection in this case, so if you apply a load, if you apply the load is acting there, what will happen? The cross section will just start deforming like this. Okay, it will just start deforming like that. Up to that point, what was happening? Up to that point, there was a deflection. It was a deformation. You can say there was. It is having deflection, and if you increase the load, deflection will increase. The curvature will keep on increasing. Okay, that is why you can see in the second diagram. This is your moment diagram, and this is your deflector shape in the elastic stage. But at the plastic stage, what will happen? If you keep on increasing the load, your deflection will be increasing, your curvature also will be increasing, right? Because the curvature is nothing but what is the curvature? That is nothing but m by ei, right? M by ei. So if you keep on increasing load, your moment is keep on increasing, and the maximum value will reach at the plastic state, mb. Okay, and corresponding to that, you can say that theoretically you can say that after that you will have large the curvature will become infinity. Theoretically, you can say that the curvature will become infinity. That indicates it has no further resistance. That is the maximum limit. If you apply further load, what will happen? It will just collapse. It is now unstable. So once the plastic hinge is formed in this structure, already I have two hinge support at the two end, and one plastic hinge is formed at the center. So now your structure is unstable. So if you apply any more further load, it will just collapse. Okay, and this unstable state of the structure we will be calling the mechanism. Okay, that is the term we will be calling the mechanism. So this we'll discuss later on in detail. Okay, so this stage of if your beam has reached this stage, then you will say that it cannot take any more load. It is a limiting stage, and if you apply any further load, it will collapse. Okay, and that state of your structure will be calling the mechanism. Okay, it is a deflector shape. Yes, it is actually the deflector shape. In the elastic stage, you can see it will have a bending and will have some finite curvature. But the moment it reaches uh, the plastic moment, it will just become like that. Whenever it will have infinite curvature theoretically, and your deformation will be something like this. Okay, and this is the region. This is the plastic hinge location. And also you can see that at this section, if you say this section will have maximum moment and it will reach mb. Okay, and this your yield moment is this section may have yield moment. Okay, and in between this section, you can say this section, the moment will be something between your m by to mb. It is a transition, we can say. This is the section we have the yield moment. Only XT fibers have reached the yield stress, and here the full section has all the section has reached the plastic yield stress, and in between we have a elastoplastic stage, partially elastic stress distribution. Okay, and this we will derive later on. What is this length? This one we will derive later on. Okay, Okay, so yeah. So simple, the plastic hinge, you need to understand only this much. The fully yielded zone of your structure is known as the plastic hinge. And once the plastic hinge is formed, it cannot resist any additional moment. And if you increase the load beyond that, the structure will just collapse. And that limiting stage, you can find out what is the corresponding load. That is your ultimate load. So you can, while designing the structure, I can design my structure based on the ultimate load. Maybe I can keep some factor of safety, and accordingly I can design my structure. And that stage, and that critical stage of your structure will be called the mechanism. And if once the plastic hinge is formed, and then we will say that a mechanism has been formed in the structure. The mechanism indicate it is corresponding to a collapse stage. So once the mechanism has formed, means it cannot take any more load. So it will not have any resistance to, it will not have any capacity to resist any further loading. Okay, so that will be your limiting condition. So while designing, you have to design in such a way that the load should not exceed the collapse load. Corresponding load will be the collapse load. So that load should not exceed the collapse load. Okay, so this is the concept of plastic hinge. Okay, it is a, you can say it is a, the plastic hinge we are calling because it will not have any resistance against the bending moment. Whatever moment it is we are applying, it is just free to rotate. It is just free to rotate. That is why we are calling it as a hinge. And there is a stress distribution, and the stress distribution is plastic. That is why we are calling it as it is a plastic hinge. Okay, so yeah, the corresponding and corresponding the load corresponding to collapse of your structure will be called in the collapse load. So while designing, we can keep some factor. I can take some factor, something like a factor of safety, and I can take some load factor actually. I can take some load factor, and correspondingly we can design. We can prevent the load will not reach. We can make sure that the load will not reach the PC value collapse load. Okay, something like your working stress method design, we usually take a factor of safety for the material strength. We usually take a factor of safety for the yield strength. So if you take a factor of safety for 2, so I will make sure that your if you take a factor of safety 2, that means for the design you will be taking only the sigma y by 2, only that strength will be considered. Okay, that is what we will do in working stress method. But here it is reverse. If you are doing ultimate load method, it is actually known as ultimate load design, ultimate load method. Okay, based on the plastic analysis and design. And here basically we are taking a load factor. I can take a load factor. I know the collapse load, but the ultimate load the structure can carry, and I can take some factor for the load, and accordingly I can design. Okay, that is another design philosophy which is known as ultimate load method. And but nowadays we are using which method? Your IS code is following which method of design? In IS code, IS 456. IS 456. We are following currently the limit state method of design. But earlier we used to have ultimate load method or working stress method also we had. Now we have the limit state method where we have some criteria for serviceability. The deflection should not exceed some value. The vibration there is some limit. So that is why we are following a working limit state method. But this is nothing but your ultimate load method design. So I can take the ultimate strength plastic moment or in the design, but I will keep some factor for your load. Okay, but in whereas in your limit state, sorry, whereas in your working stress method, I'll keep some factor for my the material strength. Okay, so yeah, we'll go to the mining part. So now we have seen how to find the elastic moment, how to find the plastic moment. We can find out. Okay. So in elastic analysis, we'll take in elastic analysis. That means your stress will be this will be the my stress distribution. Your extreme fibers only will reach yield stress, and we are finding the moment is your the bending moment at the critical point. That is your yield moment. That will be equal to sigma y into elastic section modulus. Okay, and whereas your Z E is equal to I by Y max. Okay, and in the plastic analysis, so we are following the plastic stress. This is the limiting stage, your stress distribution, and I can find the corresponding. I can find out the corresponding bending moment. Okay, and that is one of the corresponding moment of resistance. I can find what is the compression is acting here, tension is acting here. So there will be it will create a couple of equal and opposite forces acting at some distance. So it will create a bending moment, and corresponding moment of resistance, that is a plastic moment. That is equal to yield stress into plastic section modulus. Okay, and we can find plastic section modulus is at P equal to A by 2 into Y1 bar plus Y2 bar. And this is a plastic moment, it is my elastic moment. Okay, now if you take a ratio of plastic moment to elastic moment, you will get a factor. Okay, take the ratio of plastic moment, ratio of MP, plastic moment and yield moment. Okay, plastic moment and yield moment, or plastic moment and elastic moment, whatever you want, you can call KMY. So if you take this ratio, what you will get MP by MY. So that is equal to sigma Y ZP by sigma Y Z. Okay, so what will happen here? Sigma Y, the term will get cancelled, and this will be ZP by Z. And this factor we will be calling, this factor is known as the shape factor. So this factor is known as shape factor. So maybe you can check your syllabus. So you will find a term shear factor. Right? It is written shear factor. That is a printing mistake. Okay, it is a shape factor. You can check the module 3 syllabus. And this ratio between plastic moment to yield moment, ultimately it will become ZP by ZP. That factor will be calling the shape factor. Usually we denote maybe letter S, the shape factor. It is, if you want to define, you can say that it is a ratio of plastic moment capacity and elastic moment capacity. And it depends on the shape of your cross section of beam. Okay, shape of your cross section, rectangular, circular section, triangular section. The different cross section will have different shape factor value. Okay, this is a factor which is depends on your shape of the cross section, and that is why it is known as shape factor. Okay, and there's another factor is there, one more factor which we are using in the plastic analysis, and that is known as load factor. That is known as load factor. So this one I was discussing about. Finally, I can find out corresponding to that mechanism, for the plastic hinge forming stage. Corresponding to that mechanism, I can find what is ultimate load my structure can take. Okay, ultimate load, or you can say that failure load. You can call different names. Okay, and so that I while designing, I have to make sure that during the design life of my structure, it should not reach that level of load, because corresponding to that load, it will have collapse, or you can also call known as collapse load. So I should take some factor so that I can make sure that my load will not reach that collapse load at any stage, so that my structure will be safe. And that is the factor which we are using, that is known as load factor. So it is simply like a factor of safety only. The load factor usually will denote lambda. The load factor we can define, it is the ratio of collapse load. So how to find out collapse load, everything we will discuss in detail. Okay. So in this module, actually each and every terms are very important. Okay. So whatever we have discussed till now, so from there itself you will get a lot of questions when you are writing some exams. And this is also used to come shape factor, collapse load, everything used to come in form of MCQ or fill in the blanks type of. Okay. It is this module completely very, you can say very important. All the topics you have to see in detail. Okay. So it is not like just finally we'll be doing the plastic analysis of beams and frame. Only that is not the important. Everything is very important. Okay, in this module, so you should not skip anything. Okay, and this ratio, if you take the ratio of collapse load, or we can say failure load or ultimate load. You can take different name. Okay, ultimate load, or you can say failure load. All are one and same. Okay, divided by I can say it is working load. Okay, working. Just for simplicity, let me write only one term. Maybe I will write collapse load. So the ratio of collapse load by working load, and that is the load factor. Okay, and which we can say that maybe if you write collapse load by working load. Okay, this will also you can write in terms of moment. So what is the moment corresponding to that collapse stage? Your moment will be plastic moment ultimate, and working corresponding the moment corresponding to or moment resistance corresponding to your working load. That is where I can write that is a just working moment I wrote. So what is your equation for ZP? ZP is nothing but your sorry. What is your MP? MP is nothing but ZP multiply with sigma Y. Okay. And what is my MW working moment? That I can write. Okay, ZD elastic section modulus. Z is nothing but your Z elastic section modulus into sigma. Okay, it is not sigma Y because the working load can be less than the yield load also. Okay, at the stage of yield, you can say that your maximum stress is. So this is in the working condition, right? Working load. Let us say this is my stress distribution. And here I am writing that corresponding moment of resistance, that is MW, that is equal to elastic section modulus into sigma. Sigma is nothing but your extreme fiber stress. Okay, and this can be less than sigma Y. It is possible. If you are keeping a permissible stress is less than sigma Y, so that sigma will be, it can be anything. It is working load. It can be very low amount of load also. That is also possible. So sigma, I am not writing sigma Y. I am writing sigma. So now we can write here. This is an important relation again. ZP by ZD multiply with sigma Y by sigma. So what is this ZP by ZD? What is this ZP by ZD? That is known as shape factor. So that is your shape factor. Okay, this is shape factor. And what is this sigma Y by sigma? Sigma is your permissible stress, we can say, and sigma Y is your yield stress. What is that? Can you tell me what is this ratio sigma Y by sigma? What is that ratio sigma Y by sigma? Yeah, that is the factor of safety we are using in the elastic design. That is the factor of safety we are using in the elastic design, because in the elastic design, your critical the maximum stress is sigma Y. But I have to keep some factor of safety because in the elastic design, my assumption is at any stage, my extreme fiber stress should be less than or equal to sigma Y. That is if extreme fiber stress reaches the sigma Y and all other fibers inside are less than sigma Y, but that is a critical stage in your elastic design. So, but we have to take some factor safety. So that is why we will not go up to sigma Y. So if I take factor safety 2, my permissible stress will be sigma Y by 2. Okay, and this term is nothing but your factor of safety in elastic design. Okay, this is nothing but your factor of safety in elastic design. So many times objective question has been asked based on this formula only. So any one or two may be given load factor, and this may be given, you have to find the shape factor. Something like that they will frame the question. So this term is nothing but your factor of safety used in elastic design. Factor of safety used in elastic design. Factor of safety used in elastic design. And this is my permissible stress. Now we can say that this is my permissible stress. This is my permissible stress. Okay, and finally this is my equation. Okay, and the load factor, which is the ratio of collapse load by working load, and finally that is equal to shape factor in multiply with factor safety used in the elastic design. Okay, so any doubt here? Anybody have any doubt? So finally we have to remember this equation: lambda is equal to shape factor multiply with factor of safety. So you can find this question many times in your exam. Okay, this is an important relation. Okay, so this ratio also you should remember. Okay, and this is the shape factor. So any doubt? Anybody have any doubt?
No, sir.
Okay. So now we will quickly see how to. I have defined the shape factor, but now we will see how to find out the shape factor for different types of cross section. Okay, that is also simple because the shape factor, it is a factor which depends on the shape of the cross section. And how do we define that? That is the ratio between the plastic section modulus to elastic section modulus. It is coming from MP by My. Okay, and let us take a square section. First we can find out the shape factor. Okay, let us take some few section and remind things we can do that. You can, because now you know how to find plastic modulus we have discussed, and how to find elastic modulus you know. You have to just take the ratio. So maybe I can skip that one, but anyway we'll do some examples. Let me write determine shape factor. Sorry. D310. D310. Second floor. D310. 310. Okay. So I will give you a question like find out sorry yeah, shape factor for the following sections. Okay, so first let us take a rectangular cross section. Rectangular cross section. So we have already done that. So this is the rectangular cross section, let us say, and this width is B and depth is H. And what is your shape factor? That is MB by My. Okay, and this is equal to ZP by ZY. ZP. So what is the ZP? What is the equation for ZP?
P by 2 into
Final. We have already derived the final expression. What is the final expression for your plastic section modulus for the rectangular section?
B square by 4.
Yeah. So PH square by 4. Ela Elastic section modulus PH square by.
B square by 6.
So you can find the ratio, that is 1 by, it will come 3 by 2. PH square by 4. BH square by 4 divided by BH square by 6. Okay, so BH square by 6, which is equal to 6 by 4, which is equal to 3 by 2, that is equal to 1.5. Okay, that is a 1.5. Shape factor is equal to 1.5. Okay, simple. So similarly we will do the circular section. I can find out circular section also. Circular cross section. So let us take a circular section of diameter D. So my plastic section modulus we have done already. It was dq by 6. Okay.
6.
Yeah. So after some you have to, anyway now you have to, we are in the beginning, so you have to just practice all those things. After that you will remember all those equations, because that will help you to save some time, okay, in your exam. Okay, ZP is equal to dq by 6 and elastic section modulus. Uh, excuse me. Ask in office. The civil department office में first. The next room. And nine. Just wait. Hello, am I audible?
Yes, sir.
Okay. So we can find the elastic section modulus, that is I by y. I by y.
I dq by 32.
Yeah, so that is equal to, you can find pi dq by 32. So pi d raised to 4 by 64 divided by d by 2. So this is all standard result, pi dq by 32. So now you quickly tell me the ratio, the shape factor, which is equal to, just find out what is the ratio coming, dq by 6 by, you can take the value 5, 3.14 and okay, dq by 30. So give me this value, anybody?
1.697.
Yeah, so 1.697. Okay, so 1.697. So we can take it as 1.7. So many times, especially your PSC exam, like that small exam, they will ask the shape circular cross section. What is the value shape factor? That will come as a direct question. So 1.7 you should remember. Okay. Because that type of exam you cannot do this. Pi you cannot do the calculation. That will be difficult. Calculator may not be allowed. So you have to know this range. You should know 1.7. That is the range. Not the range, it's the exact value 1.7. It is 1.5. So these are all very easy to remember. You will be able to do that. Okay. And the next we'll do for maybe triangular section. Third one, triangular section. This is the cross section. And let us take the base is B. So we have done already the plastic section modulus value. We ready with that value. This is H. Okay, and we have got plastic section modulus is at P point. Some value we got 0.097976. This value is not so important. This, if you want, you can remember, but this is not that important. Okay, you can no need to remember this also. But circular section and square section, that is all important. Okay, I mean I'm talking about ZP value, set equation for ZP. dq by 6 and bd square by 4. And what's the elasticity modulus for the triangular section? I will be having the neutral axis here, the elastic neutral axis. So I by y max. I by y max. And let us say this is my elastic neutral axis. Okay. And what is the moment of inertia about neutral axis for a triangular section? What is the moment of inertia about neutral axis?
bhq by 36.
bhq by 36 divided by, what is the y max?
2h by 3.
2h by 3. Okay, you should remember that. Okay, so the result also you have to remember. These are all first year basic result. About neutral axis, your value will be bhq by 36. And if you take about base, this value will be something higher. This will be bhq by 12. Okay, so you have to remember this result. And so you can do this, and this will be coming bh square by 24, I think. bh square by 24. It will be coming bh square by 24 ZP. Because here we have written the decimal, maybe you can write here also if you want. Not so important. Finally I want to get the ratio only. If you write in the decimal form, maybe you will get something like this. Finally, it is not matter. So finally, we have to find the shape factor. That is your ZP by ZE. So what is that ratio? How much is coming? 2.34. Okay, yeah. So this is also important. You have to 2.34 you are getting. Okay. So this value you have to remember. Maybe you cannot, you don't need to remember. This is not that important. Okay, but we have to remember triangular section 2.34. Okay, and this circular section 1.7, rectangular section or square section 1.5. So many times this section, this is also it is also asked in exam, because I think this is the value, maximum value you are getting shape factor for a triangular section 2.34. That is why it has been asked many times in the exam. Shape factor for triangular section 2.34. So you are not supposed to do all those things in that exam. Okay, you should know this value finally. And the next I will take a diagonal. Next what I will do is, first we have done the rectangular section. So if you take that section, or if you take a diamond shape, something like this, let us say, and this is this height is, I'm taking h. Okay, and it is also h. Okay, and you have to find the shape factor. The shape factor which is equal to ZP by ZE. Okay, and so you have to find first section elastic section modulus. How will you find elastic section modulus? What is the equation? I by y, and this is B. It is equal to I divided by y max. So can you tell me the equation for I? What is the I value for this diamond section? Yeah.
BHQ by 12.
BHQ by 12 is only for one triangle, right?
Yes, sir. 2 BHQ.
Yeah, so 2 times BHQ by 12. Because I have taken this is h, so that I can directly use this equation. Okay. So 2 times BHQ by 12, that is what I, and I, because your neutral axis will be here only. This is your neutral axis, elastic neutral axis, and in this case it is a symmetry section. So your elastic and plastic neutral axis will be, both will be at this level. Okay, and about this neutral axis you will find out the moment of inertia, that is your I, and what is the y max? The distance to the extreme fiber from the neutral axis, that is the h. So y max is nothing but h in this case. Okay, so you can do this, you will be getting bhq by 6 by h. So bh square by 6, that is your elastic section modulus. Then you have to find the plastic section modulus, is that p, and here I have to use the equation a by 2 y1 bar plus y2 bar. So what is y1 bar and y2 bar? This is the y1 bar. This is the area, this CG of this triangle, the distance from the neutral axis, and this is known as your y1 bar. And you locate the CG of this triangle, the distance from your neutral axis, that is your y2 bar. Okay. And what is y1 bar and y2 bar? What is the equation? Y1 bar equal to how much?
H by 3.
H.
Y2 bar also H by 3.
So y1 bar and y2 bar, that is equal to h by 3. And so now I can just substitute in this equation. Okay, the color has changed anyway. So that a by 2, what is the area? That is half bh into 2, right? Area will be bh only. So area, half bh, okay, so area by 2. Okay, so area will be half bh, area of one triangle into 2. So that is equal to bh. So here area by 2, so it is bh by 2. multiply with y1 bar, that is h by 3 plus h by 3. H by 3 plus h by 3. So you will get 2 times h by 3. And finally it will be bh square by 3. Bh square by 3. So now we can take the shape factor, which is equal to Zp is bh square by 3 divided by Zd is bh square by 6, which is equal to 6 by 3 equal to 2. Okay, for a diagonal, what you will call diamond section maybe. So for this cross section it is 2, and if you keep it is in this form, the rectangular form or square form, it will be having 1.5 actually. Okay, and if you keep this orientation is a change, it will become the shape factor, that ratio between the plastic moment to elastic moment, that ratio will be 2. Okay, that means you have some moment, that is your yield moment my. Your plastic moment value will be 2 times of yield moment. Okay, that is it indicating. Okay, for a square section, your plastic moment is at 1.5 times your elastic moment. Okay, that is the meaning of the shape factor. I think you I think it is clear. So only here we have to do some calculation, and here all we already done the circuit calculation. And yeah, so now you can take any other section and you can do that. So I am not doing that. You can just solve your own. Okay, let us say we have a T section, and this is 1000 millimeter, and this is 100 millimeter, and let us take this is 100 and this is 1900, and this thickness also 100. Okay, so the cross section dimensions are given, so you have to find the shape factor. Find out shape factor. So this is just homework, you can just solve it. Okay, we have already we have discussed this. Okay, the shape factor we can say it is Zp by Zd. Okay, you locate the centroid axis, find out the moment of inertia, and get the value of I by y max. You will get the elastic section modulus. And then you locate the equal area axis, and you find out Zp by using a by 2 into y1 bar plus y2 bar. Then take the ratio, that is your elastic section modulus. That is your then you take the ratio, that is your shape factor. Okay, so you'll have somewhere maybe it is less. So somewhere here you will have equal area axis. Your equal area axis will be coming in the in the in this web area. Okay, in this here somewhere here we'll have this will be your the neutral axis in the equal area axis. Okay, neutral axis in your plastic stage. Okay, plastic neutral axis will be this one, because area has to be same. So finally correspondingly you have the stress distribution also. Your stress distribution will be something like this. We'll have compressive stress here, and we'll have like this. Okay, this is you have to locate the axis. You can do that. You can get the value of shape factor. Okay, and if you have a if you have a hollow section like this, and I have the diameter, the outer diameter is, let us say, 50 millimeters. Sorry, let us say 75. Okay, I will record. Okay, I will record the next class. So this section, let us say the diameter is given, outer diameter is given 75 millimeters, and let us say the inner diameter is given 50 millimeters. Okay, 50 millimeters. So you have to find the shape factor. Again, it is also homework. You can just find out Zp by Zd. Okay, and Zd you find out the moment of inertia I by y max. What is your y max in this case? Y max will be 75 by 2. outer diameter by 2, and you can find out the I is equal to pi by 64, d raised to 4 minus d raised to 4, capital D is 75, outer diameter, and small d is 50 millimeters, so you can get the elastic section modulus. Then you have to find the plastic section modulus ZP, that is equal to A by 2 into Y1 bar plus Y2 bar. And this one also, because the plastic, this will be the your the plastic neutral axis. So I can directly use the equation dq by 6 minus dq by 6. So maybe you can do this calculation and you will get same result. dq by 6 minus dq by 6 you have to do. Okay. So dq by 6 minus small dq by 6, dt 75 and 50. Okay, you just derive this equation. I think you will get this equation. So I think it is not coming this one. D minus dq by 6, that is wrong. Okay, check that. So this is at P. You can use this equation. You can find the total area, and you can find the centroid of this part. Okay, and this is my area like this. This is the my cross section. So this is my axis. Somewhere we have the centroid. I can find the distance, that is y1 bar. But ultimately all this will come. This everything finally this will be coming this equation only. So you can remember this equation. You can directly use the result for your solid section. dq by 6 minus small dq by 6, and then you can get the value of shape factor. Okay, and this one also you do. I will give you one more question for practice, this one. Okay, so because all this you have to do is you have to locate centroid and you have to find moment of inertia. So I am not doing all those basic calculations. You can do your own for your practice. Let us say this is 120 millimeter and this side is 150 millimeter. Okay, and maybe this is total depth is 500 millimeter. It is an I section B, but it is unsymmetric. So total depth is 500 millimeter. Okay, and maybe the thickness is given 10 millimeter. 10 millimeter. So I think this one also 10 millimeter. Okay, this also 10 millimeter. So then we can locate the neutral axis. The first you have to find the elastic section modulus, and for that you have to locate the your the centroid. So this distance we can find out y bar. So y bar you can find out. I think that is coming. I have the answer. You can try. You can solve and we can cross check. 27.2 15.2 millimeter. That is a centroid, or you can say elastic neutral axis. And then we can find moment of inertia about that axis and by y max. So we have to do the moment of inertia calculation and all. So that is why I'm not doing. So we have to spend a lot of time for that. Okay, but it is straightforward. So I am just giving you the value. Everything is in millimeter, so it is a huge value. This much millimeter is 4 by y max will be 284.3. So this is y bar 215, and this remained distance will be 284. Totally 500. So the y max will be this value, and this will give you the elastic section modulus, and this is coming finally. This value is coming as 929,929,661 millimeter cube. So we can next we have to find the plastic section modulus. A by 2, we can find the area, and y1 bar, y2 bar. So again you have to locate the equal area axis, then find the y1 bar. So maybe it will have something like this is my section. So first you'll assume, okay, I have my equal area axis is somewhere here. Then I can find this distance. Then you can locate your axis. Okay, then this area is in let us say this area is the compression area, and then I can locate the CG of this section somewhere here. So I can find the distance y1 bar. And similarly, I can find out the CG of this distance. I have CG somewhere here. I can find the y2 bar and substitute here. That is the procedure. And finally, you will get this is also coming something like 179,737.4.5. Maybe you cross check. And finally, your shape factor, the ratio is at P by It's a D, that is going to come 1 point. I don't know, I got something around 1.93. We check it. Okay, this is the shape factor. So like this, you will be able to find out the shape factor for all the cross section. But finally, for the standard cross section, you have to remember the shape factor value. Okay. So I will just give you the final result for the sum of the standard section, that you have to remember for your. I think we have 4 minute time. So this you can work out like this for any section. Whatever the cross section, only this is the steps you have to do. You can easily find out. Okay. This question is to come like this for 10 mark question or 5 mark question for the final examination. Find out the shape factor for a circular section, sorry, for a I section or T section or section like this. So this is a 5 mark question or 10 mark question for the examination. That's a lengthy question, but finally you should remember all the standard shape factor. So that will be useful for your objective exams. Okay, many times that will be asking directly, so you should know the range of values. Okay, so I will just give you the final value. You can remember that. But before that, at least once you should solve it. Okay, the shape factor for the standard shapes or standard cross section. The first we have seen already, the rectangular section, the solid rectangular section, the shape factor equal to 1.5. And second, circular, the solid circular section. So I am just shading the shape factor, it is equal to 1.69, 1.7. Okay, and next is so you can see this all in the text. You can a tubular section. You can get all this from the textbook. For the solved example, you can get tubular section. So it is impossible to solve everything in the class, and all are the same. But procedure is same. So a tubular section is like this. Okay. So it is a thin wall section. The thickness may be less. Okay, and the shape factor is, it will vary. It depends on outer diameter, inner diameter. That is it depends on that diameter, but it is in the range approximately. This is in the range of, it is around, we can say 1 point. I'm giving 1.27. Okay, and this, I think this thickness will be small. Okay, thin wall section it is actually, okay, thickness may be less. The thickness is large, then the value will be different accordingly. Okay, and another section is is very important, that is the diamond. So we have seen this is a diamond, that is a 2. This is having 2. So if you keep that your rectangular section in this orientation, you will get the shape factor will become 2 from 1.5. And another section is, I can say the triangular section. That is also very important. Okay, triangular section, that is, because this is important because it is having maximum 2.34. So I think that is the maximum value we are getting, 2.34. Sometimes that is also the maximum value of shape factor for which cross section. Circular, tubular, rectangular, square, triangular, like that option will be there. Okay, and another one is hollow circular section. So maybe hollow circular already given here. So it is around 1.2, 1.2 to 1.27, and thin rectangular section, sixth one. Okay, so this is the cross section. So thin rectangular section. That thin section means this is having thickness is very small. Okay, so the shape factor is again, it is again 1.2. So I think you can easily remember all the thin wall section, it is in the range of 1.2. So that is how we have to remember. And another one is I think it is also important, the I section. The I section maybe like this. I section. So this is my I section. So I think it is also for thin. This thickness should be less. Thickness of your I section is something less. Okay, not thick section like this maybe. Okay, the thickness will be very less. Like this may be 300 millimeter or this may be 150 and this may be 5 millimeter like that. Thin wall section. Okay, and it is having we have two axes. Let us say x axis, y axis. Oh, okay, and also I would say sometimes the shape factor you can also find about a x axis and y axis. Okay, if you want to find y axis, you have to use that result. Moment of inertia, everything should be about that axis. And this result you should remember the shape factor about x axis is around 1.12. So it is also thin wall section. It is in the range of 1.2, 1.12. Okay, that is the value I am giving. And about y axis, it will be something higher, 1.5, 1.55.